Hey everyone, in this video we're going to learn how to graph parent functions that have been scaled and or reflected. Our directions: graph the following function by first identifying the parent function and scale factor. Determine the domain and range of each function. Okay, so start by identifying the parent function. That will help us know what the graph is supposed to look like and also create a table of values to start with. Then we're going to identify our scale factor. This is going to help us take the table of values for the parent function and create the table of values for the graph we're trying to get. And then, to wrap it up, tying in that idea of domain and range. So y equals 3x squared is first. Our parent function is y equals x squared. So we have a quadratic. We know the graph is going to look like a parabola. Next, we want to rewrite it as y divided by 3 equals x squared. This form is helpful again because we can figure out how we're affecting the x's and the y values, and we have a consistent way to do it. We do the same thing with the x's as we do the y's. And reminder, the equation is always telling us how to get back to the parent function. So if we had the graph we're trying to create, we would divide the y values by 3 to get back to our parent function. Unfortunately, we don't have this. That's what we're trying to get. So we're going to reverse that idea to go forwards. So our scale factor is 1, 3. I can write this as x divided by 1, be the same thing. Okay, so the x's stay the same. We're multiplying the y's by 3. So if we had to describe the scaling, we would describe it as a vertical scaling, more specifically, a vertical stretch by a factor of 3. So now let's use a table of values for the parent function to get a table of values for y equals 3x squared. Okay, so we'll start with the parent function y equals x squared. Y, x and y. So we have -2, -1, 0, 1, 2 as our x values, 4, 1, 0, 1, 4 as our y. And then we want to create our table of values for y equals 3x squared. And to do that, we're going to use our scale factor. So our scale factor says multiply the x's by 1, y's by 3. So our new table of values is -2, 12, -1, 3, 0, 0, 1, 3, 2, 12. Well, not great because not all these points fit on our graph, but enough that we'll be able to graph y equals 3x squared and get a sense of what it looks like. So we have 0, 0, -1, 3, 1, 3, and those are the only 3 points that fit on the graph we're given. So we connect our points with a parabolic curve. So there's the graph of y equals 3x squared. The domain here is all reals, so -infinity to infinity. The range, going from bottom to top, lowest value is 0, it equals 0, and it continues infinitely up to infinity. Now, we could also plot the points of the parent function, just for comparison, 0, 0, 1, 1, 2, 1, 2, 3, 4. And we can see that the graph is being vertically stretched, so it's more narrow in comparison to the parent function. Some students like to plot the points of the parent function and do all of the work we did here on the graph. That's fine. I would advise you don't connect the points of the parent function, just so you don't confuse yourself. Hey, but you may just have a lot of points going on. So a lot of students prefer to do it in a table of values and then plot. But whatever way you feel most comfortable with is the way that I would advise you to proceed. Next up, we have y equals the absolute value of 2x. So our parent function is the absolute value of x. Now we want to rewrite this. So y equals the absolute value. Well, 2x we can write as x divided by 1/2. Again, it's really weird to do that. Not something we would instinctively think to do. It looks messier, but for identifying the scale factor, this is the best way to do that. I can write y divided by 1 if that helps. So our scale factor is 1/2, 1. So if I was describing the scaling, there's a horizontal scaling. More specifically, it's a horizontal compression by a factor of 1/2. I'm making the x values smaller by 1/2. Okay, so now we want to create a table of values. So we'll start with our parent function, y equals the absolute value of x. So we have x and we have y. Now here's where a little thinking comes in handy. Normally we would just go -2, -1, 0, 1, 2, and we could do that. But let's stop for a second and think, we're multiplying the x values by 1/2. What are the easiest values to multiply by 1/2? Well, even values. So instead of using the traditional table that we used to create this parent function, let's instead use -4, -2, 0, 2, and 4. The absolute value of -4 is 4, absolute value of -2 is 2, absolute value of 0 is 0, 2, 4. It takes a bit more work because this isn't typically what we use, but it's actually going to be easier for us in the end when we're trying to create the table of values for y equals the absolute value of 2x. So again, we're going to use our scale factor of 1/2, 1. Okay, so multiply each x value by 1/2, so that's going to be -2, y stays the same. And then we have -1, 2, 0, 0, 1, 2, and 2, 4. So these points are really nice to plot as opposed to that 1/2 we would get if we used 1 or -1. So we can plot our points. So we have -2, 1, 2, 3, 1, 2, 3, 4, -1, 2, 0, 0, 1, 2, 2, 4. Use the line tool so we have nice lines here. So we connect our points. And there we have the graph of y equals the absolute value of 2x. The domain here is all reals, -infinity to infinity. The range, working from bottom to top, is 0 with a bracket to infinity. And again, just for comparison, if we wanted to, we could plot -4, 1, 2, 3, 4, -2, 2, 0, 0, 2, 2, and 4, 4. And we can visually see that it is a horizontal compression by a factor of 1/2. Next up, we have y equals -1/3 x cubed. So our parent function is the cubic, y equals x cubed. We're going to rewrite this, so y divided by -1/3 equals x cubed. Again, we can make it x over 1 cubed. So our scale factor is 1, -1/3. And just a reminder, we don't want a scale factor to be 0, because then we'd be multiplying every value by 0, and that would create a bit of an issue. Now let's use a table of values. So we have y equals x cubed. X, y. Okay, so normally we would go -2, -1, 0, 1. But the issue is 8, -8, 1, -1. They don't multiply by -1/3 nicely. So is there a number that if we cube it, we would get a nice value that divides by 3? Well, 3 cubed would be 27. -3 cubed would be -27. That would work nicely. So we're actually going to have a smaller table of values here. We're just going to go -3, 0, 3. So -3 cubed is -27, 0, 0, 3, 27. So as I said earlier, a little thinking will save us a lot of work. So our scale factor is 1, -1/3. And we're trying to graph y equals -1/3 x cubed. Now if we had to describe what's happening, Well, I see a negative, so I know there's a reflection involved. So we have a vertical scaling, more specifically a vertical compression by a factor of 1/3, making the y value smaller. And then if we're negating the y values, that means we're going over the x-axis, so reflection over the x. Okay, so now our new points on the graph that we're trying to get, well, x values stay the same, so -3, 0, and 3. Multiply the y values by -1/3. Okay, so -27 times -1/3 is +9. 0 times -1/3 is 0. And then 27 times -1/3 is -9. So we have -3. Just scroll up for this. -3, 9, 0, 0, and 3, -9. So the graph of our cubic function looks like that. So y equals -1/3 x cubed. The domain is all reals, -infinity to infinity. And the range is also all reals, -infinity to infinity. And again, we could plot 0, 0, 1, 1, 2, 8. Although in this particular example, those points wouldn't have even helped us. So that's more on the side of the table being a little bit easier for us to utilize here. Because these points wouldn't even fit on our graph, but then once scaled, they become perfect points for us to graph. Y equals the square root of -x/2. Okay, so our parent function is y equals the square root of x. And it's pretty good, but let's write this as x divided by -2 a little bit more clearly. So our scale factor is -2, 1. The equation is telling us to divide x by -2 to get back to the parent function. So to go forwards, we're going to multiply by -2. So let's set up our table of values. So y equals the square root of x. So we have x, y. Now remember, square root of x, we want to input perfect squares. So 0, it's not a very good 0. 0, 1, 4, 9. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. And then we're trying to get the graph of the square root of -x divided by 2. Okay, so we're going to apply our scale factor of -2, 1. If we had to describe what's happening before we even graph it, we have a horizontal scaling and we have that reflection because we have a negative value. So let's see, we have a horizontal stretch by a factor of 2. We're making the x values larger. And then if we're negating the x values, that's going to look as if we're reflecting over the y-axis. Okay, so let's see if that's the case. So multiplying x by -2, so we have 0, 0 still. Then we have -2, 1, -8, 2, -18, 3. So that point won't be too helpful for us. So we can plot our points. So 0, 0, -2, 1, -8, 2. And we can connect our points. So y equals the square root of -x/2. And we do see that horizontal stretch and we see that reflection. So let's see, our domain. So working from left to right, we start at -infinity and we stop when we get to 0. So -infinity to 0, right? There's not supposed to be an arrow there. And then our range, working from bottom up, we start at 0 and we continue to positive infinity. Okay, so the square root function is one of the functions, one of our parent functions that does not have a domain of all reals. Okay, so make sure you're paying attention to that and we don't put an arrow on both sides of our graph. Next, we have y equals 4 times the cube root of 2x. So our parent function here is y equals the cube root of x, the cube root function. So rewriting it, we have y divided by 4 equals the cube root of x divided by 1/2. Again, looks a little weird, but looking at the equation, telling us divide the x by 1/2, the y by 4 to get back to the parent function. So our scale factor to go forwards is going to be 1/2, 4. We'll multiply the x's by 1/2 and the y's by 4. So now let's set up our table of values. So y equals the cube root of x. So x, y. Okay, so we only want to put in points that we can multiply by 1/2 nicely. So let's see, that's going to be -8. And then we could take the cube root of -1, but that wouldn't be nice. So we'll skip that, and then we'll go 0, and then 1 the same thing, and then we'll go 8. So the cube root of -8 is -2. 0 is 0, of 8 is 2. So then to graph 4 times the cube root of 2x, create our table of values. Okay, so scale factor of 1/2, 4. What does that look like? Okay, so we have -4, -8, 0, 0, and 4, 8. So if we plot those 3 points, so we have 0, 0, -4, -8, and 4, 8. And this is helpful this is helpful to know what this graph looks like. Okay, because there's only 3 points, so the better understanding of what this graph is supposed to look like helps us out here. So we want our graph to look like this. Okay, so that's y equals 4 cube root of 2x. Because remember, if we graph the parent function here, just to compare, 0, 0, 1, 1, 8, 2, -1, -1, -8, -2. Right? It still wants to maintain that same shape, it's just been scaled out. So our domain is all reals here, working from left to right. Our range is also all reals, working from bottom to top. Hey, but really the idea here, just to emphasize some key points, is identify your parent function, right? So we know what the graph looks like, what this table of values should be. Rewrite it in this form, where we're dividing the x and the y by the scale factor. And then just apply that scale factor to create our new table of values. Follow up on that. The more that we pay attention to what our scale factor is, the better we can set up our table of values to make our life easier, right? That's the whole idea of transformations in general, trying to make our life easy to get this graph instead of just trying to plug in x equals 1, x equals 2, x equals 3, x equals 4. We could do that. We could always do that for every graph. But can we do it in a better way? Graph the following functions based off the given graph of y equals f of x. So this is y equals f of x here. State the domain and range of each function. Okay, so we have y equals 2 times f of -x. So let's rewrite this. So y divided by 2 equals f of x divided by -1. So our scale factor is -1, 2. So that means we have a vertical stretch by a factor of 2, and we're reflecting over the y-axis. So we have 4 nice points here, and you can write them in a table of values if you find that helpful. I'm just going to work off the graph to show you a different method. So I have the point here, -8, 1, 2, 3, 4, 5. So I'm going to scale it, so -8 becomes +8, and 5 becomes 10. So I have +8, 10. So up there. Then I have -2, -1. So -2 becomes +2, and then -1 becomes -2. And then I have 2, 1, So 2, 1 becomes negative 2, 2. And then we have 2, 4, 6, 3. So that becomes negative 6. And then positive 6. 1, 2, 3, 4, 5, 6. So we can connect our points with lines. And this is the graph of y equals 2f of negative x. So the domain here, we're working from left to right. We're going to go from negative 6 all the way to positive 8. And the range, working from bottom to top, we're going from negative 2 to positive 10. So this is a really good way where they give us some crazy looking function, some piecewise function, and they're asking us to scale and reflect that piecewise function. The nice thing is they give us the starting graph or the starting points. We didn't have to come up with those on our own. So in a way, this is easier because they give us the starting point to work off of. And then we have y equals negative f of 2x. So rewriting this, we have y divided by negative 1 equals f of x over 1/2. So our scale factor is 1/2 negative 1. So we have a horizontal compression by a factor of 1/2, and we're reflecting over the y-axis. So let's start with that same first point, negative 8, 6. So that becomes negative 8, 5 rather. So that becomes negative 4, 1, 2, 3, 4, and then negative 5, 1, 2, 3, 4, 5. Then we have negative 2, negative 1, so that becomes negative 1, positive 1. 2, negative 1 becomes 1, 1. And then here we have 6, 3, so that becomes 3, negative 3. 1, 2, 3. So we connect our points with lines. So there we have y equals negative f of 2x. Our domain, working from left to right, we're going from negative 4 to 3. And our range, working from bottom to top, we're going negative 5 to 1. Okay, so that's how we scale and reflect a piecewise function. Now, 2 last questions. If the function f of x equals x cubed is multiplied by negative 8, how does the graph of the new function, g of x equals negative 8x cubed, compare to the graph of f of x? Well, if we were to rewrite this, this would be g of x divided by negative 8 equals x cubed, which would be a scale factor of 1, negative 8. So what does that mean? Okay, well, let's focus on the 8. So that means it's going to be a vertical stretch. Should probably spell that word right. Stretch. And it's reflected, if we're negating the y, is reflected over the x. So how does it compare? The graph's going to be narrower and reflected over the x-axis. Okay, so that's why I didn't write vertical stretch by a factor of 8, because we're just looking for comparison now. So we want to use narrower or wider in our comparison. And then lastly, describe the relationship the graph of f of x equals the absolute value of kx has to the parent function when k is between 0 and 1. So if we rewrite this, we'd have f of x equals the absolute value of x over 1 over k. Okay, so if k is between 0 and 1, well, that means k is 1 over k. So if k, so right now we have k between 0 and 1, that means 1 over k is greater than 1. Right, if you take any fraction between 0 and 1 and you take its reciprocal, you're going to get a value that's larger than 1. Okay, so what does that mean? Well, that means that's going to be a horizontal stretch by a factor of k. Okay, so this graph is going to be a horizontal stretch by a factor of k, which means it's going to be wider. Okay, so it's going to be wider than the parent function, which in this case is y equals the absolute value of x. So we finished this video off with a few questions to get us thinking, not just plugging in values and getting a graph out. So with all this transformation stuff, the only way to get better is to practice and work through a bunch of examples on your own. Rewatch any parts of the video that you still find confusing, and then go apply those skills to some practice problems. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.